Well, thanks for the opportunity to talk about some of our work. I'm really glad to see some of our staff members are here, so they can get to know what these poor professors and students are busy doing day and night. So my talk is on the lighter side. I think I don't have any equations. So it's more, I think Professor Ren's, what he talked about is really advanced concept. If I understand correctly, he said that in the future, right, this piece of glass can even generate electricity. And just by not even absorbing the light, so don't touch it, you can get an electric shock, right, if the charge build up like a capacitor. So here, what I'm going to talk about is still using semiconductors, that materials are in your the microchips and so on that absorbs light. But I want to talk about how we can possibly utilize in more areas, widely in terms of sustainability. All right, there are a couple of slides that sort of overlap. The sun actually gives us a lot of energy, right? On the order of 10 to the 17th watt. Okay, just to give you an idea how much the energy is. All right, so every hour, right, the energy we receive from the sun is good enough to power the entire civilization, on the planet for one whole year, right? So these few little dots, okay, add up, this area. Only in these areas, if you are able to collect the light and turn it into electric power, that's good enough to power, for the entire year, right? However, I want to pose a question to engage some of you. So if the Earth received this much energy, right, per every second, we all heard about global warming, right? Don't we worry about that the Earth want to warm up in a few months or years rather than decades? There's a lot of energy dumping down on the little planet, right? So who has an answer to that? Well, we don't need to worry about it. Well, I'll let you try. Is anyone? Is this a concern from what I talk about? There's a lot of energy, right? Yeah. If you take any, a ball, dump this much energy, it will heat up very quickly. If I don't have any volunteers, so John.
We're bright. We radiate out to space.
Okay. Yeah. He got the right answer. So the sun, right, deliver this amount of energy to the Earth by radiation, right? And this is a different spectrum, but basically show the same story as what Steve showed. Yeah. The sun, the surface is very hot, 6,000 degrees, right? So it radiates mostly in the visible, right? That's why our eye can see it. Yeah. Of course, on the planet, of course, there are the plants that can absorb the energy and convert that, into a chemical energy and so on. But most of it is really absorbed by the Earth, by the ocean, cloud, and so on and so forth. So if you cannot have a way to sort of dissipate this amount of heat, right, the Earth will definitely heat up, right? Global warming will be immediate. Yeah. And the reason that we don't have this problem so far, right, is because the Earth, we know the ambient temperature is about 25 degrees C, so it's about 300 K in this absolute temperature. Yeah. Any object, when you heat it up, it would radiate. Okay. So the Earth also radiate. Okay. It radiate in a different wavelength range. It radiate maximum the peak here. This is in the visible, right? This will be in the infrared, 10 micron. So what is 10 micron? What is this wave? That's basically heat wave. Yeah. So the Earth constantly radiate into the whole universe, right? At this wavelength. For that matter, actually, the whole universe also radiate. Yeah, this is so-called, the background irradiation, about 4K or so. Yeah. So here is I also have a pitch on the sustainability, right? So we currently, to generate this much power, right, 18 terawatts to sustain our life, is mostly by burning the fossil fuels, right? So why burning fossil fuel is so problematic? It's because it generates CO2, right? What does CO2 do? Okay, CO2 basically, the carbon dioxide actually absorbed this much, this wavelength, very, very strongly. So we have basically wrapped around the Earth a blanket of CO2. That's why we really need to minimize it. Yeah. And many times in our building, EECS building, when the last student who left the classroom, big classroom, in the evening, they leave all the lights on. A lot of our faculty and staff, right, they leave after the day, they leave the lights on. Okay. Here I want to give you some numbers, so hopefully that can change your behavior, our behavior. All right, so think about a light bulb, 100 watt, right, typical light bulb, right? If you just light up the light bulb for one whole year, how much coal does it need to burn in order to sustain this one little light bulb? Anyone have a guess? In terms of pounds, let's say? 10 pounds? 10 pounds? John, you have a better? No clue. Educated guess, please. Okay, we'll be lucky if we only burn 10 pounds. It will be over 700 pounds of coal. One light bulb, 100 watt, continuously for the whole year. So please think about this. So just imagine or visualize this light bulb is constantly giving out your CO2. Yeah. And that's only the coal, right? The coal is primarily carbon, right? If you turn into CO2, I have to add 2 oxygen. So the CO2, the weight, is going to be probably 2,000 pounds per light bulb. Yeah. So, and that's basically everyone contributing to this blanket, to warm up our planet. Okay, that's why, why we want to actually do solar, right? Solar is a renewable energy, to power the power grid and so on and so forth. But in some places, you really have to use solar. There's no other alternative. For example, the solar car, the UM has a lot of winnings. And in space, right, the satellite, there's not much options, apart from maybe nuclear, right? And in rural areas where people just don't have access to electric grid, right? Yeah. And also, of course, we would like to use solar panels, solar energy everywhere, right? There are some creative ways of making them. For example, this is so-called transparent, right? It's not really transparent. You still use these black panels, but just space them. The seams are wide enough so some light can come in. And I'm sure, I think all of us have seen the solar panels. If not, in NCRC, there is the fields of solar panels, right? Rigid, very heavy. But it will be very nice if we can actually produce these flexible, like you can just roll up, right? Then installing them on the roof will be much easier. You just climb up and spread them out, right? So there are people working on this. In fact, my lab also has some effort. So we use, we want to simplify the fabrication, right? The traditional silicon solar panel are fabricated by using semiconductor processes, very complicated. So here we also create organic solar cells. Basically, you can have a functional solar panel just by essentially coating multiple layers, like brushes, Yeah, and then it can form a working solar cell. And here we also have ways to all solution. You don't need any vacuum and so on. Just all solution process, you can actually make working solar cells. Now, even from the traditional solar cell side, you see, I actually haven't, maybe I only have seen once the solar panels in Ann Arbor that's installed on one house. Yeah, usually you don't see this. Yeah, why is that? Well, sometimes it actually it violates certain codes. For example, a certain neighborhood, right? I heard in California, they just don't want you to put this not so pretty looking solar panels on the roof. That destroyed, the sort of the view. Yeah. So that's one issue. And so therefore, you see these panels can only be put on the roof, right? So people don't see them that often. And if you think about buildings, especially modern cities, right, in Detroit, many crowded cities and so on, there are a lot of these high rises, right? And you wouldn't imagine that you want to put this black or bluish solar panel all over around the walls, right? It doesn't look good. Yeah. And you see, this is what I've found from a book. People more creative, making a sunflower type using the solar panel. These are still the black silicon solar panels, right? It's actually pretty nice, but it would be much nicer if we can actually make these sunflower blades just look like sunflower color, right? So, but traditionally this has been difficult. You cannot do it because the silicon, we want to absorb all the light, so they naturally become black, right? So that's part of our effort. We're trying to address this by creating more better looking, if you wish, solar panels. For instance, this is an example, right? We have made, my students, made these colored solar panels. They can actually be semi-transparent, right? And the way to make this, there's some detail, but I won't go into it. It's also a simpler design, right? You can just, on a piece of glass, you can deposit thin metals and few layers, basically just layer by layer, coat a few layers. And here we still use semiconductor, but it's a semiconductor that's widely accessible, amorphous silicon. Right? See, all these flat panels, your LCD panel TVs in the home, the circuitry is all made of amorphous silicon. So you can easily deposit over large areas. All right? And so it doesn't require very sophisticated fabrication like in semiconductor processing. Okay? So you can build up these layers. And they actually not only generate electricity, but have this interesting optical effect. Right? And now you can have different colors. You can piece them together to create a pattern, right? And Sean is an artist. You could actually use this to create your artwork, And this U.S. flag is actually semi-transparent. I have a sample, later on I can show you. Yeah, you can see through the water fountain right here, right? And and they do generate. Any different color, they do generate electricity, photocurrent. Yeah. So with this, we can imagine that we could put it maybe, this type of panel in many different places. Maybe even inside the home, like this window shade, right? Right now it's just passive. Right? It just absorb some light, block certain light. But there's no reason we cannot use this as an active device, not only absorb some light, but also generate electric power, right? So that'll be a pretty cool thing to have in the future, yeah. So basically, we want to make a difference with this sort of technology, rather than have these now so pretty-looking panels on the roof. Now we can change to more colored. Yeah, this is our U of M logo. It's actually I have a working device I can show you. Yeah. And in fact, my students have made a variety of solar panels based on this kind of concept. They can be semi-transparent, yeah, and they can be actually, different colors. As I mentioned, it can make fairly transparent, yeah. Transparency go, up to 70% even, yeah, and they still generate electric power. These solar panels, because they absorb certain light, reflect the rest of the light spectrum. So you could actually put multiple pieces together, right? For example, this absorbs green and reflect the rest, and you have a second cell absorb red and reflect the rest. So you have multiple pieces, put them in this fashion, cascaded fashion. You can absorb overall more light, and that we have shown that it does, and it can generate overall more power, right? So one possibility is the high-rise building I showed earlier. Maybe one building coated is a green type of cell. The neighboring building coated with a blue type of cell, right? Yeah. So because the light can bounce back and forth. Yeah. So here's how you utilize the natural sunlight, right? But there are many other areas where we can really harvest the light, right? Inside the room, for instance, there are plenty of light. And another thing is like the display. The panels are getting bigger and bigger. There are plenty of light, in fact, that are totally wasted. I just want to put in one slide on the liquid crystal display structure. Is this is competitive to the Samsung cell phone. Yeah, it's basically there's a backlight. They use these so-called polarizers and color filters to give rise to the colored display, right? I think LCD display is still the dominant type of display on the whole. Every one of us have multiple of such devices. So it uses a backlight, white backlight, as a light source, and coming out through multiple layers and eventually reach to your eye. Yeah. How many people actually know what is the power efficiency of this type of device? Suppose we have 100% white light, backlight. How much light can we see actually with our eye? Want to have a guess? He left. Otherwise, want to have a guess? This, by the way, this LCD display is after half-century development. It's got to be good, right? 20%. Yeah. No, not ow. I mean, that's his guess.
I say 80.
Okay. You say 80. Okay. If any one of you, okay, are able to make a 80% or 20% panel, I can probably guarantee you're going to be the richest person in the planet very, very soon. Okay, because so many people are using these. Yeah. Kind of pathetic. It's only 5-6%. All right. So huge amount of light is totally lost in these few layers, because traditionally, these polarizer color filter, the reason they, for example, it shows blue because it absorbs the rest of the light. That's 2/3. Huge amount of light totally wasted. Yeah. So from this point of view, one could think about, well, maybe we can put this photovoltaic solar cell kind of concept to even these display panels, right? This is something that we did a few years back. Yeah, we tried to make these colored pixels at the same time while inserting these semiconductors so they can actually produce electricity. That's some of the photocurrent that we showed earlier. So that's another way. There are other areas where you really can absorb, harvest the otherwise wasted light that turns into heat, right? Okay. So I just want to have a couple of slides showing that after this work and then simultaneously, I guess there are a lot of people interested in developing, the colored panel and so on. Recently, couple months ago, I saw a news from our neighbor, MSU. There was a professor's team developing I believe it's a colored solar panel. I haven't read their paper so far, but I can show you a similar work that this was published very recently, from Swiss Center of Electronics and Microtechnology. So they have shown that they are able to make this colored as well as white solar panel. Right? There's a team holding a large piece of a white solar panel. And how did they actually accomplish this? Rather than I talk about it, there's a video. You can. This is my. I think this is my. Oops, holy.
CSEM introduces a revolution. White and colored solar panels for use everywhere. Until now, solar energy has been synonymous with blue-black solar panels that cover buildings and devices with a monotone hue. Not anymore. Our revolutionary technology lets us achieve what was supposed to be impossible. Solar panels with no visible cells or connections. Solar panels can now disappear. A rainbow of colors means solar technology now serves aesthetics as well. Solar modules can be integrated and customized everywhere. We can change the color of all existing panels or create customized looks from scratch. It's a simple, magical solution. Our mastery of different technologies makes this possible. Our solar modules are very sensitive to infrared light. This passes through our special film, which reflects all visible light. It's easy, adaptable, and low cost. A bright new horizon for solar energy everywhere. CSEM's photovoltaics, redefining impossible.
I thought it's this show up. So basically, the way it works is that they use traditional solar panel like silicon, right? But they put these filters, we call it filters, on top of it. So basically, the top layer either scatter or reflect the visible light that our eyes can see, but it passes infrared light through that layer. And this infrared light get absorbed by the solar cells. and that generates power, right? So you just put a passive type of filter on top of a solar cell. Yeah. Of course, the efficiency will be lower because it's only absorbed. Remember that solar spectrum, the infrared part of the light. Yeah. So, yeah, I think since the video didn't show, there's a lot of development, by the way, in solar cell field. This is tracking from the 1970s, all type of cells and so on, right? And they are cells that are actually not getting 90% efficiency that Steve talked about, but pretty high, 45, 80%. This is using very complex and expensive technology. And these type of cells can only go up, to power the satellite and so on and so forth, right? But even recently, you see, you look at the curve that has a very sharp slope, right? That's latest and very promising technology, like these 3 dots, right? Yeah. So this is using a semiconductor called perovskite. My lab also work on some aspect of this. Yeah. You see, this is a very sharp trend. Yeah. And the efficiency going up within a short few years period of time. So there are plenty of research that need to be done, including some really innovative ideas like what Steve talked about, yeah, to really push this technology, so we can have hopefully less coal to burn. Think about that light bulb, right? Yeah. Yeah, that's the end of my talk, and I'll be happy to answer some questions.
But by this time you're thinking, boy, this is complicated. Why do these guys go to such trouble to do this at all? We already have solar cells.